It's a pleasure to welcome Chris McKee for this week's Origins Colloquium. Chris was my PhD advisor, so I'm very grateful he can give us this talk today. Chris received his PhD from UC Berkeley in, I think, 1970. I was just looking at the title here, Study of the Two-Stream Instability in Colgate's supernova model of cosmic ray acceleration. And then, of course, has gone on to work on many different topics within astrophysics. After Berkeley, as I understand, Chris, you were at Caltech for a year before joining Harvard's faculty for a few years before fairly soon returning to Berkeley.
That's correct.
And at Berkeley, then you appointments in both physics and astronomy, and including, I remember during my thesis being the chair of when you were the chair of the physics department. Particularly known for many aspects of work on the interstellar medium, but also outflows, high energy astrophysics from relativistic outflows, and reverberation mapping of active galactic nuclei, and many other topics in star formation in particular. So, Chris, it's a pleasure to welcome you here and hear about your work on the first stars.
Okay, thank you for the kind introduction, Jonathan. So, first, let me talk about, contrast the formation of the first stars versus stars today. So today, as we know, stars form in giant molecular clouds. And the typical size, these clouds have a radius of a few to 50 parsecs. Their mean density is around 100 to 1,000 per cubic centimeter. And of course, clouds today have metals, that is, heavy elements in them. So the gas is molecular and can cool to about 10 Kelvin. And the dust can further cool the gas and shield it from radiation. Now, if we go back to the very first stars, theories assume that we have cold dark matter. And so the first stars form in cosmic mini-halos, that is, condensations of dark matter that have formed from the initial fluctuations in the universe. And it's very important that so far there's no direct experimental evidence for cold dark matter. So it's always important to keep this hypothesis in mind when we're talking about the theoretical work on the first stars. Now, these cosmic mini-halos in which the first stars are thought to form have a total mass of, say, 100,000 to 1 million solar masses. They're 100 parsecs in size. And I emphasize here, I'm talking about physical units here, not co-moving units. The variable velocity is of order of 5 kilometers per second. And the initial gas density is about 1 per cubic centimeter. So, yeah, I'm trying to good. Then you have gas inside this mini-halo when it contracts. But because there are no metals, it can't cool that much. So it cools maybe to a couple hundred to 1,000 Kelvin. The Bonner-Ebert mass, that is the mass that can resist the contraction due to gravity, at a couple hundred degrees, around 500 solar masses. And the gas is mainly atomic for densities less than about 10 to the 10th. There's a recent, very comprehensive review of the first star formation by Clausen and Glover, just came out this year. And, whoops, now it's not my, oops, okay. There we go. Okay. So if you look at the strength of the magnetic field, in order for stars to form, you have to have that the gravitational force exceed the magnetic force. So it has to be what's called magnetically supercritical. The mass to flux ratio has to exceed a critical value. And I'm showing this the data for the nearby galaxy from Crutcher on the right here. So you have the line of sight magnetic field is measured from the Zeeman effect, which on average is half the total field strength. And it's plotted as a function of the column density and sort of divided into two parts. The low column density region is mainly atomic, whereas the high column density region is primarily molecular. And you can see that, roughly speaking, consists with having a constant field of order 6 microgauss in the atomic gas, and but having a magnetic field which increases with column density in the molecular gas. So magnetic fields also drive protostellar outflows. And here I have both observations on the left from an ALMA observation from the Class 0 source in Orion, and on the right, a simulation, a 3D MHD simulation of a rotating disk wind. And it's also rotating. And you can see the lines there are the magnetic field lines. So how do magnetic fields affect the formation of the first stars? So this is sort of an outline of my talk. First, I'm going to talk about the origin of magnetic fields in the universe, focusing on the Biermann battery. Then discuss the turbulent dynamo, which amplifies the field. Then to give a theoretically predicted simulation of cosmological dynamo versus an actual one. In other words, what we did was we wrote a paper in which we used theory, both of the theory of the dynamo and theory of the simulation, to predict what the actual simulation would give. And so we'll compare those, and then discuss the effect of magnetic fields on the formation of the first stars, and with conclusions. So I've given some references here at the bottom. So Kulsrud and Anderson gave a discussion of the nonlinear growth of the dynamo. I'm sorry, actually they included the kinematic dynamo and nonlinear phase. Then there are two important papers by Xu and Lazarian. In the 2016 paper was a comprehensive discussion of the dynamo action, both from beginning to end. And then in 2020, they showed that because of the lack of flux freezing, you did not have a normal magnetic field going like density to the 2/3 power when you have gravitational contraction. Then there are two papers that I participated in. The theoretical paper where we predicted the outcome of a simulation, that's MSL20, and then in Athena Stacy et al. In 22 was the actual simulation. So let's begin with the origin of magnetic fields in the universe. And there are two possibilities. There's a quantum origin in the early universe versus a classical origin after recombination. So the quantum origin requires effects beyond the standard model. Now, it's important to keep in mind that we know that the standard model is not complete. So the fact that it's beyond the standard model doesn't mean that it's impossible. On the other hand, the standard model does explain all existing, at least particle accelerator data. So during inflation, if that occurred very early, then you have to break the conformal invariance of the electromagnetic field. So conformal transformations leave angles between the corresponding curves unchanged. In particular, the light cones are invariant. So it's interesting that in this was a very early paper by Mike Turner and Woodrow in '88. And they pointed out that there are a lot of things that are not conformally invariant. On the other hand, I would think that preserving light cones is very important. Anyway, so we'll have to wait for advances in theory in order to see whether this holds up or not. Now, another possibility is that later on, during the QCD or electroweak transition, if it is a first order phase transition, but again, in the standard model, they're not. So in a QCD transition, for example, you take into account the fact that the force between the quarks is very small when they're really close together, and it gets stronger and stronger as they separate until at some point around 10 to the minus 13 centimeters, the force saturates. And so what happens is that at very high densities and very early in the universe, then the quarks are so close together that the quark-quark force is negligible, and so they don't really feel anything. And at some point, as the density goes down and the separation becomes a order 10 to the minus 13 centimeters, then there's a transition in which they go into nuclei. Okay, the classical origin I'm going to talk about is the Biermann battery. So let's discuss that. And this was proposed by Biermann in 1950, and then wrote a paper with Schlitter a year later in 1951. So normally we think that the astrophysical plasmas have no electric fields, but that's actually not true. They do have electric fields in order to maintain electric neutrality. So I've written down the electron equation of motion for the case where there's no magnetic field, and also there's no radiative forces. So we just have the pressure gradient in the electrons and the electric field acting on the electrons. Now, the mass density of the electrons is negligible, so we can just set that term equal to 0, and that tells you that you get an electric field which is proportional to the pressure gradient in the electrons. And that, in turn, if you take the ratio of the electron pressure to the density, that's just the same as the total pressure to the density if the ionization is constant. So if we just say that the gradient of the pressure is a word of the pressure divided by the length scale, and the pressure is nkt, so the n's go away, you can see the electric field then is a order kt over EL. So the associated potential EL is a order KT over E. So if you have a temperature, for example, of 10,000 degrees, that just means that the typical potentials inside the plasma would be of order 1 electron volt. Okay, now we know that if we apply Faraday's law, if E has a curl, it's going to generate a magnetic field. So we have that the partial B with respect to T is just proportional to the curl of E. Well, we know what E is, and if I take the curl, if you take the curl of the gradient, that's 0. So what I get is the curl acting on 1 over the density. So we got the cross product of the gradient of the pressure times the gradient in the density. Now, I repeat that equation here. And the important thing to note is that if you have a barotropic fluid, which normally we consider, where you have the pressure is a function of the density. So for example, we have an adiabatic gas, so P goes as the density to the 5/3 power, then you can see that the gradient and the pressure will be parallel to the gradient and the density, and so you get 0. However, in curved shocks, you naturally generate magnetic fields. So the pressure is order rho v squared. The shock thickness is written down as lowercase l. That's very small. And the radius of curvature of the shock is on a much larger scale. So if I then just write down to order of magnitude what the top equation is, I have B over time, and the time is just L over V. And then that's of order, we have the pressure there, which was rho V squared. And so that gives me a mass of the hydrogen atom. I get the V squared, I have the C. The densities cancel out, and I get the 2 length scales. So solving for magnetic field, I find that basically the magnetic field is a fundamental constant times V over L. So for galaxies, Biermann and Schlitter estimated of order 5 kilometers per second velocity, size scale of a few hundred parsecs, and therefore they concluded the field that would be generated by this mechanism would be around 10 to the minus 19th Gauss. And then they estimated that a small scale dynamo could amplify that to of order 10 to the minus 7 to 10 to the minus 4 Gauss. So I think that's really quite remarkable. This was done over 70 years ago. And so they got the same value that I'm going to get in just a moment for the first stars. And then for the final field, the observed field is a few times 10 to the minus 6, which is right in between the 10 to the minus 7 and 10 to the minus 4. So that was a pretty amazing paper. Okay, so let me summarize where we are so far. So it's possible that magnetic fields originated in the early universe, but that requires physics beyond the standard model. And all astrophysical plasmas, except for paraplasmas, have electric fields that keep the electrons and ions together despite the low electron mass. The Biermann battery is that if the electric field has a curl, it will generate a magnetic field, and curved shocks do this naturally. Biermann and Schlitter estimated an initial field of 10 to the minus 19th Gauss in the galaxy, which is comparable to our estimate of the field that exists on a scale of 100 parsecs in a cosmic mini-halo in which a first star formed. Okay, so now we have this tiny field, and we have to get it up to be significant. And so we talk about the turbulent dynamo. And there are 2 phases of this dynamo action. The first one is the kinematic dynamo, excuse me, which the field is so weak that it does not affect the dynamics. So we're going to discuss this with ideal MHD, so that means we're going to neglect the resistivity. We're also going to assume that the turbulence is subsonic, which means that the divergence of the velocity is 0. It's incompressible, approximately. So the electron equation of motion but now we're adding in the a magnetic field, but still neglecting radiative forces is given there. And outside curved shocks, then when we take the coil of this, the gradient of the pressure is going to vanish. And we just get the curl of E plus V over C cross B is 0. So if we apply Faraday's law and also take advantage of the fact that the divergence of V is 0 and also the divergence of the magnetic field is 0, you can write down the equation where the, here's my arrow there. Oops, that one. And you get the equation then written down for the partial B with respect to T. And so then the total time derivative of B, I bring over the V dot grad B to the left-hand side. And I wind up with the total derivative just goes like B dot del V. So what does that mean? So B dot del means I'm taking the gradient along the magnetic field. So first imagine that the velocity is parallel to the field. Then what this says is that if the velocity, say, is changing along the field, the field is going to get amplified. And there's a children's toy that you may be familiar with where you has a tube, you stick a finger on each end of the tube and you pull on it and the tube will shrink. And so the same thing is going on here. You bring in field lines will then contract toward the axis here. Now, on the other hand, if the velocity is perpendicular to the magnetic field, then what this gradient is going to do is cause the field to bend. And in principle, it can actually even fold over. So now I'm repeating what I've just said. So we have that the curl of E plus V cross B equals 0. And with Faraday's law, we got the total time derivative of B. So now I'm going to multiply by the magnetic field. And that gives me the time rate of change of the magnetic energy. And because this derivative is proportional to the quantity itself, that means that it grows exponentially, and the growth rate is given by this expression for gamma. And as I've just described, B dot del V both stretches and folds the magnetic field. So since subsonic turbulence has a velocity that goes like size scale to the 1/3, the fastest growth is on the smallest scale, the viscous scale, where the L sub nu, where nu is the kinematic viscosity. And as a result of that, you can show that the magnetic field grows like E to the gamma nu T, with this gamma sub nu being the V over L at this very small scale. And that can be written in terms of the Reynolds number in that expression there. And as you probably know of, the Reynolds number in astrophysical plasma is very large. So this gives you a very large growth rate. So then what happens when the magnetic field grows to the point that you get equipartition on the scale of this L sub nu, the viscous scale, then you enter a nonlinear phase. And this can occur when the magnetic energy is order 1/2 V squared on that scale. And the idea there is that the energy in the eddies of scale L is transferred to the field at a rate 2V over L. The 2 is because it's an energy, so it goes like V squared. And then that means that if you write down the time derivative of the magnetic energy, you have the 1/2 V squared is the energy you have, and I'm transferring it to larger scales at this rate, 2V over L. And that gives me a V cubed over L. And in Kolmogorov, in a very famous paper establishing the theory of subsonic turbulence or incompressible turbulence, showed that V cubed over L is a constant in that turbulence. So what that means is that the magnetic field grows linearly with time in the nonlinear dynamo. And eventually it approaches equipartition on the outer scale of the turbulence. So now, again, let me summarize where we've gotten to for the turbulent dynamo. For negligible resistivity, Faraday implies the exponential growth of B with this growth rate, which is of order the eddy turnover time. And the most rapid exponential growth is due to the smallest eddies, and that gives you a growth rate which is proportional to the square root of the Reynolds number, which is large. The nonlinear dynamo starts at equipartition at the viscous scale and grows linearly in time until it reaches approximate equipartition on the outer scale of the turbulence. Okay, so now we're going to talk about the theoretically predicted simulation of a dynamo in star formation versus the actual simulation. So the key point is that the kinematic dynamo, as we've said, has a growth rate, goes like the square root of the Reynolds number. The Reynolds number goes like inversely with the viscosity. So that says the growth rate goes inversely with the viscosity. Problem is that when you're doing a numerical simulation, the numerical viscosity is much greater than the actual viscosity. So, for example, for SPH codes, I've written it down using numbers which were characteristic of our simulation. And then we got a number which was order 10 to the 23 centimeters squared per second for typical parameters. The actual viscosity for neutral atomic hydrogen is orders of magnitude more than 1,000 times less. And so the actual growth rate, which goes like nu to the minus 1/2, is 50 times the numerical one at a density of 1. And then as the density goes up, the disparity becomes even greater. And that means that you have to begin a simulation with an artificially large field. So this is then the theoretical prediction. As you have plotted the magnetic field versus the density. So if going up in terms of magnetic field, at the bottom I have the Biermann, the initial Biermann field, which we've discussed. Then Kulsrud pointed out that the turbulence would cascade down from this curved shock and amplify the field as it went. So you get a sort of amplification of a factor of about 1,000 due to that. Then you would have the kinematic dynamo until you reached this nonlinearity at the viscous scale. And after that, then in addition, because we're doing a star formation simulation, we're having gravitational collapse. So the density increases. And we assumed that this would increase as the field would go up like the density to 2/3 until it reached equipartition. And once it's in equipartition, that says that B squared goes like the density. So B is n to the 1/2. So what is the situation in a simulation? Well, the axes are not the same here because now I'm plotting B over the 2/3 power of the density to take out that part of the variation. But I want you to notice on the left-hand side that if I divided by n to the 2/3, the vertical line would have been unchanged. That is basically constant density. So that says that in reality, the kinematic dynamo is so fast that it occurs before there's any collapse. But because the numerical viscosity is large, the growth is much slower in the simulation, and you actually get a substantial increase in the density. And this parameter phi sub ff is since in the theory, we didn't really know how fast the cloud would collapse. So we just parameterized it in terms of the free fall time. So that's a big problem. So to do our simulation, what we did was we used Gadget 2, which was a hydrodynamic code, but that Athena Stacy had been using, and to do a cosmological SPH simulation. So we implemented a new method for kinematic MHD, starting at a redshift of a little over 50. And then once we got to the point that the magnetic field had grown to a value that it was starting becoming nonlinear, we switched over to a high-resolution adaptive mesh refinement simulation using our code Orion 2. The resolution there was 3 AU in an 0.5 0.5 parsec box. We followed this simulation for 9,000 years, after which the first star formed, and then continued the simulation for 2,000 more years. So this is what we found in terms of the field. The little dots are the field at the different points in the simulation at the end of the SPH simulation. And our theory is the blue curve, the fit to the simulation, or the red sort of strange, not dashed, anyway, red dotted line. And it agrees quite well with the theory, except at the very end, you can see that the theory is predicting a slightly higher value field in actuality. Then we have the end of the 2/3. If you didn't have any dynamo amplification, that's what the field would look like. So clearly the dynamo has amplified the field by a factor of over about 1,000. And then there was an earlier paper by Turk et al. And they chose a weaker initial field, so that then it was always in the kinematic phase. And the dynamo amplification ceased at about 10 to the 7th, where our kinematic assumption breaks down. So then we predicted in this 2020 paper, the prediction was based on Kohlrausch and Anderson 92 and Shu and Lazarian 2016. We assumed flux freezing and the gravitational collapse of the first star, and we then determined or made estimates for the numerical viscosity in both the SPH and grid-based code. So the simulation revealed that we had to make two necessary corrections. The kinematic dynamo was slower than predicted, and flux freezing actually was violated and reduced the growth rate of the nonlinear dynamo. And that was, in fact, work done by Shu and Lazarian in 2020. But we sort of after we'd completed our theoretical prediction. So here's what we found. On the left, this is when the zinc particle first formed. And the top then is the thermal specific energy. And the blue dashed line is the kinetic specific energy. And then you have the black line is magnetic specific energy, which is basically the square of the Alpine velocity. And you can see it by the very end, the magnetic energy is dominant. If we go to look at this as a function of time and look at the high density gas, you can see that at the time after about 1,000 years, the magnetic energy is dominant. Okay, so what's the summary here? Excuse me. The simulated kinematic dynamo is much slower than the real dynamo because currently the numerical viscosity is more than 1,000 times larger than the actual viscosity. The combined cosmological SPH simulation starting at Z of 100 with a high resolution AMR simulation at redshift of 27.5, we found that the growth rate of the kinematic dynamo is reduced. So the coefficient of gamma nu is smaller than predicted by the theory of Shu and Lazarian in 2016, presumably because the numerical resistivity is significant. In their theory, assumed that resistivity was negligible. With that adjustment, our theory and the simulation agree on the kinematic dynamo. So we confirmed the prediction of Shu and Lazarian that flux freezing is violated in the nonlinear dynamo that resulted in a slower growth of the field in a contracting medium. Okay, so this simulation was really to try to see the effect of magnetic fields on the formation of population 3 stars. So these stars have no metals except possibly lithium plus metals secreted from the interstellar medium. So no population 3 stars have been detected. They would have a mass less than 8/10 of a solar mass. So here I've given some data. The most metal poor star I'm aware of has a metallicity of about 10⁻⁴. The most iron poor star has an iron abundance of less than 10⁻⁷.3. And one of the things that is puzzling is that you'll see that the references are a decade or more old, and people are looking very hard for these stars. So I think it's remarkable that and with all the work that's going on since then, these, as far as I know, still seem to be the most metal poor stars. The question is then, why is it that there are no low mass stars observed today? Now, it's possible that some of these galaxies, these are little snapshots of galaxies observed by JWST, might actually harbor population 3 stars. And hopefully we might learn something from analysis of these data. So when we did our simulation as I mentioned, we had a cosmological simulation, and then we moved over to an adaptive mesh refinement MHD simulation. And that included the hydrogen and deuterium chemistry and cooling. And the results of our simulation were that after the first sink formed at, we call that t equals 0. And what we plotted here is the accretion rate onto that sink for both the hydro case, that's the blue, and the MHD case is the black. And you can see that the total accretion rate onto all the sink particles, although there's usually only one in the MHD case, is about a factor of 2 less for the magnetic fields case. So fragmentation is substantially reduced in the magnetic case. So I have 3 curves here. If I look at the first, let's look at the blue curve, which goes up to a total of 12, it looks like. That was when we did a hydro run. And then we have the black line, that is the MHD run. And you can see that around 350 years, there's, we have a total of 2 stars, but the rest of the time there's only 1 star. So really almost no fragmentation. Then the black dotted line is an earlier simulation that Athena did that had higher resolution of 1 AU and included radiated feedback. So it had more fragmentation and fewer mergers than our run with AMR. So as I've emphasized, only a couple of stars formed the MHD run and they rapidly merged. So the magnetic fields reduce the fragmentation by reducing the density. So what when we create sink particles, when they're less than 4 finest grid cells per gene's length, or a gene's volume of less than 64. This had been recommended based on simulations, earlier simulations by Federath et al. So we exclude magnetic fields from sink particles, and that's because if you look at stars today, they have very weak fields compared to the field they would have had they retained their interstellar field. And I note that this is opposite to the assumption in the recent simulation by Hirano and Machida. So the critical mass for gravitational collapse includes both the magnetic effects and the thermal effects. And so what we looked at the density in the cube in our simulation that had the largest ratio of mass to the critical mass. And you can see that the blue dots are generally higher than the solid black line. The hydro gets to higher densities. So on the right, we plot the ratio of the mass to the critical mass. And the blue dotted line, which goes up high, is the hydro case. The black line is the MHD case, and the red dashed line is just the part of the MHD case that is for the thermal part, thermal pressure. And you can see that only the hydro case reaches density greater than the critical density, triggering the formation of sink particles. So the final mass distribution at 2,000 years after the formation of the first star, if you look at the red lines, that's the mass distribution for the hydro run, and there's 1 star that we have for the MHD run. And the maximum masses are actually similar, about 26 solar masses. On the right, I show the results from Sharda et al. They have a couple of papers. And you can see that if you look at the top, that is the IMF. The axis there on the bottom there is the sink mass, and then they just have the number of stars plotted. So it's a very top-heavy IMF. It peaks at around 5 or 6 solar masses. But they have many stars that are less than 0.8 solar masses. So in contrast to us. But they carried out a much larger number of simulations. They had a slightly lower resolution than we did. And as I said, they found that the magnetic field had a significant effect, but less than the effect that we found. On the other hand, in a recent paper by Prohl et al., they concluded that magnetic fields do not affect the first stars. So the conclusions for my talk are, first of all, that it's possible that magnetic fields were produced in the early universe via phase transitions or during inflation, but these processes are beyond the standard model. If fields of order 10 to the minus 19 Gauss have not been produced by the time of recombination, they will be afterwards by the Biermann battery in curved shocks. Then Faraday's law implies exponential growth of the kinematic field in a turbulent medium. And so that just gives you written down what the growth rate is, and it goes like the square root of the Reynolds number, where the Reynolds number is large compared to 1 in astrophysical plasmas. So in our SPH plus AMR simulation of a kinematic dynamo, we found that the growth rate, as predicted, was much slower than a real dynamo, because currently the numerical viscosity, which is determined by the resolution of the simulation, is more than 1,000 times larger than the actual viscosity. So it's our results for the kinematic dynamo were slower than predicted by Shu and Lazarian, presumably due to the effects of numerical resistivity, which they did not include. Our simulation, however, did confirm their prediction from their 2020 paper that flux freezing is violated in the nonlinear dynamo in a contracting medium, resulting in slower growth of the field. So we carried out the first cosmological MHD simulation of the formation of the population 3 stars, combining the Gadget 2 SPH with kinematic MHD from redshift of 100 to 27.5. And then an Orion adaptive mesh refinement simulation with full MHD for 11,000 years around the time of formation of the first sync. And our results are consistent with a very top-heavy IMF. Only 1 star formed with a mass of 26 solar masses after 2,000 years, consistent with the absence of observed population 3 stars. Now, other simulations of magnetic fields have disparate results. So Sharda et al. Found a top-heavy IMF, but formed stars less than 0.8. I note they did not include stellar mergers. Saad et al. Found evidence that magnetic fields make the IMF more top-heavy. They focused on the role of the field geometry, but they too found lower mass stars. And Hirano and Machida found that magnetic field suppresses fragmentation in disks. However, Prohl et al. Found no effects of the magnetic field. So the primary challenge in further studies of the formation of the first stars is that we need a substantial increase in the numerical resolution in order to accurately simulate the turbulent dynamos. So that I conclude there.
Great. Thank you very much, Chris. So we can now transition to questions and discussion. So if you have a question, please raise your hand. People in Virginia and Chalmers there also help me coordinate here. And while I wait for some people to raise their hands, let me ask then first, Chris, if I understand correctly, this the turbulent dynamo in the kinematic phase is very fast. Is it always then fast enough to amplify to near equipartition within a free fall time? Or do you require?
Yes, well, the kinematic dynamo, remember, stops at the time when you have equipartition at this very small length scale, the viscous length scale. So it definitely, that time is very short compared to the free fall time. Then you go into the linear growth in the nonlinear dynamo. And in that case, the growth that we found that the adiabatic compression of the field dominated the nonlinear dynamo, but that's because we used we assumed flux freezing and had the magnetic field growing as the density to the 2/3 power, whereas Shu and Lazarian, when they allowed for violation of flux freezing, found that the field grows more slowly. So then the dynamo action could be relatively more important.
Mm-hmm. Okay, I just take them in order. So Naoki first, and then Gina.
Yeah, thank you, Chris. It's nice, very nice summary, and I have many questions. But so Chris, you also mentioned this, but I find a slight discrepancy between Shu Lazari and your result, and actually the argument of Shu Lazarian was the nonlinear regime, where actually the B field grows linearly with time. They said it was more extended, and that's why the saturation level is not achieved. But you said something slightly different, didn't you?
No, I had a linear, when we're not talking about a contracting medium, so we're talking about their 2016 paper. Yeah, I think we got that, that was consistent. When And when we're doing the simulation, the nonlinear dynamo is coincident with the gravitational contraction. And because we assumed that the magnetic field was going like the density of 2/3, that tended to dominate the nonlinear dynamo. Whereas had we used, excuse me, their result for the contraction, then I think the nonlinear dynamo would have been relatively more important.
Okay. One more technical question. So usually we assume a Kolmogorov type turbulence, but I kind of suspect in the virialized halos, the turbulence is not really subsonic, and maybe even the spectrum might be closer to Burgers. And what do you think about this?
Yeah, I think that if in our results, let me see if I can go back to that. Oops. Now, I somehow have lost the ability to, yeah, there you can see, if you look at the left, the thermal specific energy is the green. So that is large compared to the kinetic energy.
Okay.
So at least in our simulation, then it's closer to Kolmogorov than to
Okay. Okay. Yeah.
Can I
That's
just
I
ask,
see. Yeah.
can I just ask a point of clarification then? So is Lazarian saying that the field diffuses? Is this anything to do with reconnection diffusion, or is it why does flux freezing not to happen?
Yeah. So in their picture, it is what they call reconnection diffusion. And one of the problems that I've always had with their discussion is that a lot of times they appeal to reconnection diffusion, but they never actually put in a diffusion. So, and in this case also, their derivation there's no diffusion term in their analysis. But instead, excuse me, they assume that as it's contracting, as I recall, assume that the characteristic scale varies as the Jeans length. We had proposed a slightly different version, which is an equally good agreement with the data, where it just sort of this characteristic scale just goes with the co-moving scale, and that also does the same thing.
Okay, so we can maybe come back to that, but let's have Gina go next and ask.
Yeah, hi. Thanks for your talk. So I have a somewhat naive question. I'm thinking to get the magnetic field to do something in this stage, you need some level of ionization. And I'm wondering, what do we know about the ionization level of the gas? If we don't know much about the ionizing photons, but by how much can we twiddle with that ionization fraction? How much does that make a difference in the end?
So we assumed ideal MHD, so we're not really able to deal with the effects of low ionization on the evolution. So the ionization in remember, since we're forming the first star, there is no UV radiation. There's no ionizing radiation. And we're assuming that at least up until 2,000 years after we formed the star, that it's so the mass is large enough to make ionizing radiation, but the accretion rate is so large that such a star would be very puffy, and the temperature would be too low to produce ionizing radiation. So in our model, the electrons are basically just left over from recombination.
I see. Okay, thanks.
But you do have a chemical model, I would assume. When you're following the chemistries, you are predicting the ionization fraction.
That's right. Yeah. So we followed the chemistry. That's correct. I'm saying, but there's we don't have any, once you get, because the temperature is low, there's no new ionization. As my recollection is, the temperature never gets high enough so that collisional ionization is
Right.
important.
But you can evaluate to what extent ideal MHD is a good approximation. I think it's still pretty good, isn't it?
Yeah, we did not do that. So when you get to the very highest densities, I don't know what the answer would be.
Great. Chun Yan?
Hi, thank you for the nice talk. I have the two questions. So for the theory part, you assume that there is the incompressible plasma, right? So that is also true in your simulation.
I'm sorry. So what is true in the simulation?
Because I see in your theory part, you assume that is diverse V equals 0. It is also true in your simulations.
Yeah. So in the as I said, we had two different codes. In the SPH code, we developed, because it was not the version of the SPH we had was a hydro code. So we added in a kinematic MHD, and then we did divergence cleaning to ensure that the magnetic field, was divergence free. Then in the AMR code, that uses constrained transport, and so it guarantees that the field is divergence free.
Okay, thank you. So my second question is that you discussed about for the numerical simulation, you have some numerical viscosity. So because you use the AMR technique, so it is the estimated, you said the numerical viscosity is probably 10 to the 3 or 10 to the 4 order of higher than the theory, but it is true for every different size grid.
Well, no, I didn't give you the formula for the numerical viscosity for the AMR case. So if you go to high enough resolution, then you can make the numerical viscosity as small as the real viscosity, but that would require a much higher resolution, and therefore, much longer computation. But if you look in the paper, the reference, our 2020 paper, then in appendix, we give the results for both the numerical viscosity, SPH, and for grid-based codes.
Got it. Thank you.
Well, perhaps I can just follow up on that. I was surprised to see that you're actually not too far away from, well, your factor of 1,000, was it 1,000 below where you need to be? So perhaps you can comment on what how expensive the simulation would need to be to resolve the viscosity, to resolve the dynamo action.
Yeah. So let me see do I have see that this for the SPH, it goes like the SPH particle mass to the 1/3 power. So if I wanted to prove things by a factor of 1,000, I would need to make my particle mass 1 billion times smaller.
Ah. Mm-hmm.
And so I don't, like I said, I didn't write, in the interest of time, I did not do the grid-based formula, but it's also, excuse me, very challenging there as well.
Mm-hmm. And I guess AMR wouldn't particularly help in
Yeah, what the formula I wrote is gives you the result for the finest level of AMR.
Mm-hmm. Great. I'm just checking if there are other questions in Virginia or Chalmers. Then maybe
Can I ask you one more question, sorry, Jonathan.
please. Yeah, we have time.
Yeah, so Chris, a bit advanced question. So the in the dense protostellar disk, at some point there can be magnetic braking, and accretion rate is affected unless the things like ambipolar diffusion can occur. So what do you think about this when you the fragmentation part, that is okay. I'm almost sure I agree with you, but the accretion rate in a magnetized protocell disk can be more better accurately evaluated by, I don't know, with non-ideal MHD or considering some other effect. What do you think?
Well, can I
Yeah,
also?
no, I completely agree that I think that in order to treat the disk, you would have to include non-ideal MHD. So our resolution was several AU, and so you wouldn't really trust anything less than about 10 AU. And
do you have a disk, Chris?
yeah, we did have a disk, but it was not well resolved. Also, because remember that the disks tend to have a thickness which is, maybe 1 or 10% of the radius. So when I say that we, resolve the vertical structure of the disk also becomes very challenging.
But the size of your disk depends on whether you have the field or not. Is that right?
We did not actually make that comparison, so I don't know.
Because my understanding of fragmentation in these kinds of simulations is that it's disk fragmentation, from what I recall, generally. So it is the.
Yeah, we had some disk, but we also had just more sinks forming in different places in the simulation. So
So
yeah, trying to
even in the hydro case, you
remember. So if we also implemented a merger criterion, if they got if 2 sinks got within 4 cells, then we merged them.
Let me see. I have still some questions here, but I guess because we looked at this with Eric Blackman a long time ago, but I'm not sure we did exactly, because it's 20 years ago now. We relied on the disk dynamo to I think we thought we needed the disk dynamo rather than the kinematic dynamo, but we may have used a different scaling. But that of course requires a rotationally supported disk to form. I suppose if the field is not weak enough, then a disk will form. You could always amplify it in the disk dynamo, and then one difference of the disk dynamo could be the ability to generate large-scale field, which then would be helpful in an outflow. Did you see outflows beginning to form in your simulation?
No, we did not see outflows. So you're making a very important point. That was which is the geometry of the field. The small scale dynamo is going to generate a tangled field, which is presumably less effective in generating outflows. So in one of the Sharda et al. Papers, they said that they found evidence both for a small scale dynamo and for dynamo action in the disk. And we did not attempt to draw any conclusion like that.
I mean, that is very hard to resolve because of the disk scale height and the stratified disk.
I agree.
Okay, any other questions? Let me ask then, why? Well, I mean, there are different results from the different numerical simulations, which seems a little strange, like why that is. But also for local star formation, some groups have been able to reproduce the IMF, without magnetic fields. Matthew Bates' work, and I've always been curious about that. I don't know if you have a thought here. So just by having a dynamically important field, you completely change the IMF here in your model. So
that's a very good point. So the conditions for the first stars are so different. I mean, the temperature is more than order of magnitude larger. And another important point is that the initial conditions for the first star formation are dominated by the gravitational potential of the dark matter halo, not by self-gravity, whereas, of course, in contemporary star formation, it's all self-gravity. And I'd like to make it, I don't know how this would affect the results, but my understanding is that our simulation is unique in that it does follow the evolution of the field in over cosmological times. We initialized our field at a redshift of over 50. And a lot of the other runs, the papers that I referenced, will just start insert the magnetic field at the redshift where the star is forming. And whether that, so that is a difference between our simulation and the others.
So you're saying when they see fragmentation, it's because their field has not been amplified quickly enough to reach?
No, they put in a strong field. I'm just saying that they do not put in a self-consistent field. Our field was evolved self-consistently over cosmological times. And whereas what they do is they assume a field that is close to equipartition and put in, assume that it's turbulent and so forth. And then they do allow the field to grow, but it grows only over hydrodynamic times, not over cosmological times. Whether that makes a difference, I don't know. I'm just pointing out that is a distinction between our simulation and the others.
Okay, we're coming near the end here, so any last questions for Chris? Let me ask at least one more here then. If I wanted to magnetize the intergalactic medium, can I rely on this dynamo action in lots of different mini halos, or do I need to eject it from galaxies?
So because and I think this is an issue that Naoki has also worked on, there's actually a flow of the gas relative to the dark matter halos. And this will generate widespread turbulence. I do not know the filling factor of that turbulence as to whether it would eventually fill the volume of space or not.
Naoki, any comment before we finish?
Yeah, I think, if I look at my calculation, up to 10 to the minus 22 or minus 21, this level can be achieved in even like a low density IgM. Although mine is for 1 megaparsec box. So for very large.
And it fills space?
Yes.
Oh.
Yeah, that is. Yeah, it's just a misalignment between the pressure gradient and electron density gradient, and that's mostly everywhere. The strength or degree differs from place to place, but to some extent it really exists.
Great. Well, if there are no further questions, all that remains is for us to thank you again, Chris, for a great talk and discussion.
Okay, well, thanks for having me.